Hello everyone. Today we are going to give a presentation about the solving method for this assignment. For solving the problem of sending essential supplies to the boys who are trapped in the cave, designing a supply box which is able to withstand the underwater pressures and build using the minimum amount of material is necessary in order to keep it lightweight and easy to handle.
So here's the question 1 given. Then, this is the situation that we imagined, which is deliver the supply box to the junior football team that trapped in the cave. And here are the box properties that given by the questions, which is the volume and the dimensions of the supply box.
In this video, we are going to touch a little bit about the optimization theory. Let me briefly explain about this. In my own words, optimization is just like shopping in a mega mall. Let's imagine a set X filled with choice. Let's say this set X is all the types of commodity in the mega shopping mall, and there are various types of commodity such as food and beverage, stationeries, furniture, makeups, and skincare products, clothing. While you might be tempted to choose what you actually like and ready to purchase, we haven't finished setting up the optimization problem yet. For the optimization problems, we need context. This context is given by a function fx equals to y, where y is a totally ordered set. With this example, we could define f as being the function representing your top Asian type mom's ranking of these commodities. You ask your mom to rank these commodities by assigning the numbers y equals to 1, 2, 3, with 1 representing the best, and the result which come out from you might be f clothing equals to 1, f food and beverage equals to 2, f furniture equals to 3, f makeup and skincare products equals to 4, f stationery equals to 5. In this case, it's trivial to see that clothing is the best choice. While it would be great to have a mom available anytime to provide trivial solutions to optimization problems, in reality, we almost always need to do this work ourselves. Therefore, we need to understand how to set up an optimization problem so that we can find our solutions. Formally, an optimization problem can be defined as given a function f mapping a set S to totally ordered set Y, find the bets as star which is elements of X, where bets is defined by f so that fx star lower or equals to fx for all x which is elements of bit x. Refer back to the last example. The clothings could be set as the best choice, which is familiar to the maximum value as we know in the map, while the stationery will be the minimum value at here. This is called extrema. It is widely used to solve problems involving efficiency, cost, profit, area, and other quantities. Seen exhaustively, comparing all choice is infeasible. We need to find a way to limit our search place. Calculus provides us the tools to do just that. For this session, we will assume that f is a real value function defined on real number choices. We will further assume that this function is twice continuously differentiable. And also, for the optimization problem in calculus, the derivative is set to 0 because it identifies critical points, which is potential location where a function may have a maximum or minimum value. After that, we are going to perform second derivative test to check the concavity to determine whether the value is a local minimum or local maximum based on the situations f prime prime x higher than 0 and f prime prime x lower than 0. In summary, optimization theory uses derivatives to locate and analyze points where functions achieve their best or worst values.
First of all, with the intention of designing the supply box with minimum amount of material, The supply box should be a rectangular box with square bottom and a volume of 0.5 meter cube. Therefore, the equation for the surface of the box should be formulated first in order to find the dimensions of the box that require minimum area. From the information given, we can know that width of the box is equal to x, length is y, and height is z. So, we can form an equation of the volume of the box, which is v equal to x, y, z. Since it is a square bottom, we can assume that x equal to y. Thus, we will come up an equation which is v equal to x squared z. Then, substitute 0.5 as the value of b into the equation. After that, we could get an equation which is z equal to 0.5 over x squared. Then, we need to form the equations of the surface area of the box, which is a equal to 2xy plus 2yz plus 2xz. After that, substitute x equal to y into the area equation, and we will get a equal to 2x squared plus 4xz. Subsequently, we can substitute the equation z equal to 0.5 over x squared into the surface area of the box, which is a equal to 2x squared plus 4xz, and we will get a new equation a equal to 2x squared plus 2 over x. After we gain a new equation, we need to apply differentiation to solve this optimization problem. By using differentiation, we could get the first derivative, which is di dx equal to 4x minus 2 over x squared. Let the first derivative equal to 0, so that the value of x can be obtained. So we will get the equations for x minus 2 over x squared equal to 0, and we multiply these equations by x squared. So we will get x 4x cubed minus 2 equal to 0, and we shift 2 to the right and shift 4 to the right in order to get x cubed equals to 1 over 2. At the last, shift the cube to the right hand side. So we will gain the x value, which is 1 over cube root 2. Next, we are required to undergo the differentiation one more time in order to gain the new equation, which is d squared a over dx squared equals to 4 plus 4 over x cubed. Perform the second derivative test as the x value again to check whether it is maximum or minimum by substituting 1 over cube root 2 into the second derivative. We will get the value of 12, which is the answer after substituted. And we know that for the value of second derivative bigger than 0 is minimum point, while for the value of second derivative smaller than 0 is maximum point. From this calculation, we could see that it is a minimum point. Therefore, the area built is undeniably the minimum area. So we can confirm that x must be the minimum width with the value of 1 over cube root 2, and by using the equation x equals to y, so y also equals to 1 over cube root 2, then we are substituting the x value and the y value and the volume into the v equals to x, y, z equations. Then we can do some rearrangement, so in order to get the z value. So we got the z value 1 over cube root 2. So the final answer of the dimensions of the supply box that require the minimum area is the xyz equals to 1 over cube root 2 meter. Alright, now let us move to the part 2 question. So here's the question 2, and with some drawing that represent the Roman 1 and Roman 2. For this section, we will have to consider the total hydrostatic force that's acting on the vertical surface. Before we calculate the total hydrostatic force, we would like to explain some theory about this total hydrostatic force. The important theory in this section would be the weight density and the fluid force on the vertical surface. For the weight density, it is a multiplication of the density and the gravitational accelerations. While for the fluid force acting on the vertical surface, because liquids are nearly nearly incompressible, and the pressure on any part of an object, horizontal or vertical, at the same depth is the same. This formulation of the force on the side of a vertical surface works. The pressure exerted on the enclosed fluid is transmitted undiminished to all parts of the fluid and the walls of the containing vessel. As the French scientist Blaise Pascal 1623 to 1662 noted, Pascal principle is the name given to this outcome.
About the part 2 question, there are two types of conditions about the total hydrostatic force that is acting on all the vertical walls of the box, which is when the base of the box is at a depth of 5 meters submerged in normal fresh water, while another condition is the base of the box is at depth of 7 meters submerged in muddy fresh water. The main difference we have noticed is that the density of the fresh water and the muddy fresh water at 25 degrees Celsius is 1000 kg per meter cube and 1078.5 kg per meter cube respectively. At first, let us discuss part 1. To calculate the weight density, we need to apply the formula of weight density equals to density multiplied by gravitational acceleration. So, the density equals to 1000 kg per meter cube multiplied by gravitational acceleration of 9.81 meters per second cube square is equals to 9810 newtons per meter cube. Next, we need to utilize the formula about calculating the fluid force on a vertical surface. The formula is given below. For calculating fluid force on a vertical surface, we need to find the width first since it is not mentioned in the question. Assume that A equals to negative 5 meters and B equals to negative 5 plus Z. After substituting the value of Z into the equation, which is the cube root of 1 over 2, we can find that B equals to negative 4.2063 meters. Therefore, until here, we have got all the values required for calculating the fluid force on the vertical surface. We can simply substitute the values inside the equation to get the fluid force acting on each vertical surface. Density is 9810 newtons per meter cube. With Wx is the cube root of 1 over 2 and Hx is x. In this equation, we have to undergo integration by increasing the power of x from 1 to 2 and also divide the whole terms in the integration by 2, which is equals to the power of x after integration. Also, don't forget to put the modulus in order to ensure that the values coming out will always be positive. Therefore, the value of hydrostatic force acting on each vertical surface is 28,447.04652 newtons. One more important thing, since the value of fluid force acting on each vertical surface is calculated for only one vertical surface, we need to multiply this value by 4 to represent the 4 vertical surfaces. Ultimately, we will obtain 113,788.1861 newtons as the total hydrostatic force. Now, let us move into the next part, the condition where the base of the box is at the depth of 7 meters submerged in muddy fresh water. As we mentioned before, the density of muddy fresh water is 1078.5 kilograms per meter cube. Hence, the weight density is 10,078.5 kilograms per meter cube multiplied by 9.81 meters per second square equals to 10,580.085 newtons per meter cube. Besides, we have to find the value of point B in y-axis as well. Assume B equals to negative 7 plus height, substitute the value of depth and height inside. By this, we could get negative 6.2063 meters as the value of B with negative 7 meters as the value of A. By now, we have already gathered all the information required for the calculation of fluid force acting on the vertical surface. Referring back to the earlier equation, substitute the values of B and A, 10,580.085 as weight density, cube root of 1 over 2 meters as the width, and put x as height since we want to find the fluid force acting on the vertical surface at point x. Also, integration inside the equation should be done while the division of the terms of x by 2 is required, and the application of modulus is necessary to gain a positive value, which is 44,010.20264 newtons. At last, all we need to do is to multiply the fluid force acting on the vertical surface by the number of vertical surface, which is 4, for obtaining the total hydrostatic forces. As you've seen in this calculation, the final value of total hydrostatic forces acting on the box while submerged in 7 meters of muddy fresh water will be 176,040.8106 newtons. And that's all from us. Thank you guys for paying attention on this video.